Hi, welcome back to Act 2 of Hijax. This is Lecture 9, High Branching Computation. So Act 2 has been all about how to master writing programs that have computational graphs that are going to work with tracing and compiling under Jax's just-in-time compilation. But if all of our programs have to be flowing through the same computational graph, independent of the values of the inputs, what happens to branching, like if statements? One of the most fundamental elements of control flow in programming. It's like one of the first things you learn when you're learning Python is how to branch your computation using if statements. Well, if statements are evaluated at trace time, just like other things in Python, like for loops, and that means that we can only use them to branch if the conditional in the if statement is computed based only on statically available information, like static inputs and the shapes and data types of dynamic inputs. And so if we want to effectively branch our code and do sort of effectively different computational paths for different inputs, and getting the effective if statements, then we're going to have to learn a few new tricks. And today we're going to explore basically a few of those tricks through the context of implementing one of the most fun things that programmers can do, which is building a video game. Well, it'll be a very simple video game, the kind that is studied in reinforcement learning. However, before we get jumping into that, we're going to have to go to spend some time in the JIT dojo to master some more details of branching and how it interacts with JIT. So let's get right into that. So I'm here in the Hijax repository once again, and I'm back on my MacBook Air today because we won't be doing any big transformer training today. And I'm going to go straight into the JIT dojo. And today we'll be looking at our final two lessons in the JIT dojo, lessons 6 and lesson 7. So let's start with lesson 6. So lesson 6 is, actually, my mistake. We've already done lesson 6, haven't we? We're just looking at lesson 7. That's going to be a lot faster then. So lesson 7 is that we can't branch on dynamic values. And so I already sort of hinted at this just now, but let's see this in action. So if I run lecture 7, Python and run lecture 7, lesson 7 I should say, then we're going to get an issue. And so I think we should basically just take a look at this and see if we can fix it. So what is going on here? So we have a function that we're defining. Just like before, it's going to be a function that basically involves we have an integer array, and we're going to be computing as output another integer array. And let's see, because we were able to run this function a few times before we get this error, which we actually sort of expect here in the code. So let's run up to that point and then eventually see what happens. So first of all, we define this function and then we call it without JIT. And so what happens when we call this function without JIT is, as you would expect, we'll go through and what is marked here as tracing time is actually going to be happening in real time and in line with debug time because we haven't JITted this function. So tracing and debug statements are going to happen as the program is interpreted by Python. And so what is going to happen is we're going to see that, first of all, our first thing that happens is we print the value, ignoring this sort of trace directive, we print the value of a, and we've given it, unsurprisingly, this input of the array 1, 2, 3, 4, and so it has the value 1, 2, 3, 4, and we see that's working. We can get n, which is the array A's shape, and we're not printing that out. We're then going to have a look at the value of the first element of the array and whether or not it is greater than 0. And I've called this variable pos0. So if we're positive in position 0, then this will be true, and otherwise it will be false. And it looks like if we print it out, we see that it is in fact true. So of course 1 is greater than 0, so that should be the case. And then it looks like we then have a branch in our program. So if n is greater than 0, which means that we actually have something at this value, and then if pos 0, which means if we have at least one value, and then in that position we have a positive value, then I'm going to be returning a. And otherwise, oh, sorry, this is just the array that was the input. And otherwise, I'm going to be returning the negative of the array that was input. And so what this basically does is, I guess, returns like an absolute value of the array. It's not quite an absolute value. It's more like a lexicographic absolute value, where you could have negative. If you interpret the sign of the array as being sort of the sign of the first element, then this is going to normalize the array so that the sign of that element is positive, but all of the relative signs of things are going to stay the same. It's not quite a lexicographic absolute value because we aren't handling the case where the sign is 0, in which case lexicographically we'd have to look at the rest of the elements, like one after another, and see until one was positive. But anyway, it doesn't really matter what this function does. It just sort of matters that we understand a little bit how it's implemented, and then we can interpret what's going on. So here's another example where we call the function with a negative array, or at least the first few elements are negative, and importantly, the 0th element is negative. And so we go through the array and we realize that pos0 is false. And then when we are going to return it, we're going to return the negated version of the array. So it's going to be normalized so that the first element is positive, as we said. Okay. So now the next thing we want to do is transform this function with JIT and call it again and see what happens. And the spoiler is that we're going to get an error, and this is going to be an error that we're risking seeing like many times in our JAX programming journey. And so it's good to become familiar with it, because this is a good one to look out for. So so we're transforming and calling the function again. So we JIT it, and then when we call the JIT version of the function with an array, we're going to get immediately an error before we even see any tracing or printing or anything like that. Actually, I guess we do see some tracing. So the error comes up during the trace pass because we get some of the trace output. We know that the A is a JIT tracer. It's an abstract int32 array of size 4. That makes sense. We're already quite familiar with how tracing works in JAX, and this is sort of to be expected. And of course, then, if we are to look at the position of that array, we will see that we should have a scalar, because we're basically taking an element of an int32 array, comparing it to 0, and we're going to get a scalar, and it's going to be a Boolean scalar. So JAX is able to figure that out without knowing what's in the array A. I suppose when I wrote this, I was sort of thinking maybe you should guard against the case where the array is empty and indexing is going to be a problem. I think JAX and JIT is actually going to sort of handle that case a little bit differently, and it's best to just make sure it doesn't happen rather than trying to guard against it. And this ended up being not very effective because we're checking the size, but then we're immediately indexing anyway. So in order to evaluate this pos0, we're going to need to check. So that's my bad. But anyway, have a look here. When we print out tracing, then we see that that the position is now no longer true or false like it was previously, true or false. It is instead an abstract Boolean scalar. And then here comes the part where we can check n greater than 0. That's no problem. But when it comes time to check and pos0, we get this error. So let's read the error. Tracer bool conversion error. Attempted Boolean conversion of traced array with shape bool. The error occurred while tracing the function blah, blah, blah. We know where it came. This concrete value is not available in Python because it depends on the value of the argument A. So this is another kind of, it's a bit like the concretization type error that we saw in a previous lecture. In this case, we're seeing a bool conversion error where we've tried to access the concrete Boolean value of an abstract Boolean scalar. And that is required because Python needs to know that Boolean value to evaluate this and we need to evaluate the and to decide which branch of the if statement we're going to take. So right off the bat, we're seeing that if we want to take a branch based on a dynamic value or anything derived from a dynamic value, we're going to hit this kind of error. And that is an example of what we can't do in JAX. You can do it if you're not JITting your program, but you can't do it if you want to also compile your program, if you want to use JIT. And we normally want to use JIT, so this is a problem. And that's all I wanted to show you in the JIT Dojo. Why don't we step on over to lecture 9, if I get out of the JIT Dojo, and into lecture 9. I have here a script called environment.py. And the environment script is basically the demo for today, is that we're going to implement a grid world maze environment. Well, it's not going to be that much of a maze until the next lecture, where we'll learn about some maze generation algorithms. But for now, it's going to be a grid world, and there will be a few obstacles, and this will be about sort of creating a system that can kind of move around, where an agent can kind of move around this grid world, and it can't walk into walls and so on. And in order to do this, we're going to need to have conditions all over the place. When we want to interpret an action, we're going to need to make sure that the agent, the hero character in our little game moves up if the action was up, moves left if the action was left, and so on. And we're going to need to make sure that if the hero tries to move in a direction where there's a wall, then the hero doesn't move at all. Otherwise, they'd be walking through walls. This is the kind of thing that is going to look superficially like we need to use branching and if statements. But we're going to see ways to make this just like any other computation in JAX. Let me be clear. Actually, when I say that the computational graph is not allowed to branch depending on dynamic values, that's true. But remember, the computational graph doesn't mean all of the computation. Many of the computations that we do in JAX programming involve different values coming out depending on the inputs that come in. Of course, if you add two numbers together, the result that you get is always going to depend on the inputs that you put in. So the only thing we need to be careful is that we make sure that we're using these kind of operations that can be parallelized when we want to decide what input should come out. And they don't have to be linear operations. They don't have to be standard arithmetic operations. There are actually some operations that we can access through the jax.lax API and the jax.numpy API that will allow us to decide based on abstract Booleans, as in based on dynamic Boolean arrays, whether a choice of two values should be in an array. And that is going to be what we'll be looking at today. And we're going to need to do a bunch of that in order to get this little hero to be able to walk around a grid world. So let's start with looking through what code we have here. We have very little code compared to some of the previous lectures because we're kind of taking a step away from deep learning and the kind of neural networks that we've been building up over time and the optimizers. And we're taking a step in the direction of deep reinforcement learning. But before we do deep reinforcement learning, we need some environments. And so we're building the first of those environments today. And this is going to be, what we've got is a bunch of inputs. The only sort of new ones here are that we're using pillar again, which will be useful for saving some animations later. And we need NumPy also for processing images to save those animations. The main is currently empty. We're going to implement a bunch of stuff. And then we have some code here that's a little bit tedious for kind of arranging some stuff in a grid and printing it or saving it as a GIF. So let us get started in basically implementing the environment. And so let me give you sort of a high-level overview of what we're going to implement. We're going to implement a object or a class that is called environment, and it's going to be a pie tree, and it's going to basically have what we need for implementing. Hold on. I'm very sorry. I've lost my code that I was looking at. There it is. Sorry about that. We're going to implement an environment class, and it's going to have methods for kind of tracking the state of where the hero is in the world and where they're going and all that. And we're going to sort of be able to use this environment analogously to a neural network parameter. So when we have a neural network parameter, we can randomly initialize it, and we'll randomly initialize a world where the hero is going to be standing somewhere and trying to get somewhere else to a particular goal in a grid world. And then we're going to be able to update this with various inputs. But instead of gradients, we're going to be updating this environment using actions that would be, in reinforcement learning, these actions would be chosen by a policy. Or if you're playing a game, these would be the actions coming in from your controller. And so we're going to implement the various sort of aspects of this environment and also the rendering of the environment so that we can see it on the screen in front of us. And so that we can sort of have a window into what's going on in this little world. And so let's get started with that now. And so the first thing we need to do is we're going to need some randomness. So I'm going to need a random key. So I've got my seed here coming in from Tyro. And so I might as well just use that to jax.random.key with this seed. And then we want to sort of do what I said. We want to initialize this environment. and we will then probably want to render it. So I'm going to define an API here that I'm then going to implement afterwards. So let's start by defining the API by just saying what we would like to exist. So let me say if I had a random key, and I could jax random split my main key in order to get that. And then maybe I could have this thing called a state, which is going to come from an environment. And this environment is, I'm going to want to init it, and I'm going to want to init it by passing in this key init. And then, do I need to pass in anything else? Yeah, probably I want to know how big is this environment going to be. And so we'll have a static argument that comes in that is the size. It's going to determine basically the size of the world that we're going to have. And by default, I'm setting this size to 12, which will be sort of not that big that it will just easily fit on the screen and we'll be able to see everything in this world. Okay, and then once I have speaking of seeing what's going on in this world, once I have a state, I want to probably be able to render it. So I want to have maybe something like state.render, and I want to be able to, I guess I don't necessarily need to pass anything as input, but I want to be able to print this out. And maybe I'll make it return an image, as in like an RGB array. And then I can make it that I can use matplotlib to print that as an image. So matplotlib image will give me a matplotlib plot, which we'll be able to print to the terminal like this. So now what I need to do to live up to this is I need to define an environment, and I need to have a static init method, and I need to have a render method as well that works on a method that works at the level of an actual instance. And so let me make a new section of my code here and say this is going to be the section where I define the environment. And you know what? We're in the habit of making everything a pie tree when we can. So let's see if we can also make this a pie tree. So tree-util.register data class. And we'll say this is data classes.data class. And we'll say it's a class we're going to call environment. And we know that we need to make a static method that is called def init. And it's going to have to return self. And it's going to take input, we decided, a key, which is a PRNG key array. And it's going to take a size. And yeah, I think we should probably, the size is going to be an int. I think we should probably get in the habit of jitting our methods as we go. So let's make sure that we jit this, wrapping it in jit before we wrap it in static method, because we can't jit static methods. Let's jax.jit this, but we actually need to use functools partial. Functools in order to jax.jit it, because, well, maybe I don't need so much space, because we need to flag a static arg name that is going to be size, because I'm telling you that the size of the environment sort of variables is going to depend on this size parameter. What are the environment variables? So let's define those. Let's sort of define the fields of this data class. And so one thing that you might like to have in your environment is a hero. And we already talked a little bit about the hero. So the hero is maybe going to have a coordinate that represents their position in the world. So let's call that hero pos. And let's say that's going to be an int array, and it's going to have shape 2. So like an x coordinate and a y coordinate. And then maybe the hero is trying to go somewhere. That's normally what a story or a game is about. And so let's say that there's a position of a goal, and that position is the game will win the game if we can get the hero to the goal, basically. And then it wouldn't be a very interesting game if there weren't also some obstacles. So let's make walls, and let's make this a bool array. And let's make basically the size of the world this can be like the map. And we'll make it that most of the squares in the grid are false in that they don't have a wall, and then some of them are marked true where there is a wall. And so where there's a wall, then we want to make it that the hero can't go through the wall, they have to go around. And then they have to sort of navigate their way around this world and get to the goal. And so that is going to be what our environment comprises. And a particular environment object is going to represent basically the state of this system, where the hero is, where the goal is, and what the world is like, where the walls are. And so this init method, its job is to basically come up with a hero pos, a goal pos, and some wall positions. And we're going to do that randomly so that every time we play this game, it's a little bit different. So let's start by generating the wall layout. And And so there's a couple of different ways you could generate this, but here's the way that I came up with that made a little bit of sense to me. We're going to start with walls as just like a blank array. So we're going to make it zeros of the size. And this is why we need size to be static, because now we're seeing that some of our variables in our computational graph are depending on, their shape is depending on the size parameter. So we want to make sure this is jnp.bool. Actually, I think we just use bool from Python if we want that. And then this is not a very interesting world because there's no obstacles at all, but it is at least a world, so it's a start. But we can make it a little bit more interesting if we add some walls. And the first walls I want to add are going to be around the boundary of the world. So I want to make sure that definitely the sort of the top row and the bottom row and the left and right columns always have walls in them. So we can't go walking the hero off the world. That would be disastrous if that happens. So let's make sure that we can say walls at those positions. So what are those positions? I said the left, so the top row and the bottom row, and for all of the columns, we're going to set those to true, and that will put walls in the top row and the bottom row. And then we'll do walls equals walls at for all rows, I want to say the first column, that is the leftmost column, and also the rightmost column, the last column, I want to set those to true as well. So this should make it so that I have my walls going all the way around the world. And on the corners, I've kind of double set them to true, but obviously that will have no effect. And I'm remembering just to note that because walls is immutable, because it's a JAX array, I have to use this pattern of .at.set in order to actually modify it. This will create a new version of walls. So I've created in total 3 versions of this walls array with progressively more walls in them. Okay, this is like constraining us to the grid, but it would be nice if we had maybe some obstacles inside the like arena that is left by that. And so for that, I guess we probably want to do some random placement of walls. And so we're going to need to fork our random key. So let's take a key for the walls from our random key and say jax.random split of our key in order to get this. And then let us now randomly decide for each grid cell whether or not we should put a wall there with some probability. And I don't want too many walls, so I'm not going to make the probability too high, and I want them to be independent. I don't want there to be any kind of correlation between different positions at this stage, although we'll next lecture look at making more structured kind of wall systems and mazes. But for now, I think the appropriate thing to use is going to be the jax.random Bernoulli. So I'm going to say we don't need to worry about the outer walls. They're already definitely all there. But these inner walls inside the sort of the remaining space, the size -2 by size -2 grid that is on the inside of these exterior walls, we're going to sort of decide for each of those squares whether there's a wall there. And the jax.random Bernoulli method is going to allow us to create a vector of Booleans with an independent probability of each one being true. So jax.random Bernoulli is going to be what we want, and we'll pass in our walls key. And then we'll pass in this probability that we want. Let's set it to like 0.1. And then we have to decide what shape we want. And I'm saying we want size -2, size -2, which will be the right size to sort of fit right in between these walls that we set manually. And then we can take this and set it to the walls that we have that we've been building up, this actual grid, by saying walls.at. And we just have to slice out this interior section. So square bracket 1 - 1 will be like the second, or I guess this way, the second row all the way to the second last row. And then in the other direction, in the columns direction, we have to do the same thing, 1 to -1. This will get the second column all the way to the second last column. And so we've kind of we've sliced out this interior portion. And that's where we want to set this to inner walls. I'm not sure if this is the first time that we've been setting something other than a scalar, but if so, obviously you can just do that. You can do anything that you could do a NumPy style assignment if you were mutating the array, you can use set for that. And so here we see an example of that. Okay, this seems to be basically the wall arrangement that we want. It still remains to generate a random position for the hero and the goal. And then we'll move on to actually rendering this world so we can see it come to life. But at the moment, you're just going to have to use your imagination that we've built up this like structure. I guess it's just an array. We could like print out this array, I suppose. But we need to get through to finishing the actual init method before we do anything else anyway. So let's generate a random hero and goal position. So let's say we're going to do this as follows. We're going to take all of the positions that are in the interior, and we're going to decide to put the hero in one of them and the goal in another one of them. And then if there was a wall there, that would be a conflict. We'll just like delete the wall then if there was a wall there. We can do that easily enough. That will make it pretty easy to randomly decide these positions. There's a couple of other ways you can do this, including like getting a list of all of the positions that don't have walls and randomly choosing one of them and using that as the position. But I'm going to go with this method because I think it will be slightly easier to code right now. What we're going to do is we're going to number these positions in the interior by basically like a number between size minus 0 and size minus 2 squared, not including the upper bound. And that will number all of these things. So let's see if we had to grab some of those indices. We would need a key, which we'll call the position key or key pos. And we'll split that off our normal key. So jax.random.split key. And then we're going to generate these indices, which are going to be these numbers between, in this case, I guess it's like 0 and 99 because size is 12, and so size minus 2 is 10, and so 10 squared is 100. And so there's 100 positions in the interior, and we just have to decide one of them, or two of them, I suppose. So we'll use jax random choice to decide a random 2 of those. And so jax random choice, of course, takes a key, and we'll use our key pos. And then it's going to take a sort of array that we want to choose from, or an integer representing the indices, like in the A range, if we wanted to choose just a random index into an array. And so we need to put size minus 2 squared here. And then we need to say how many of these numbers do we need, how many of these choices do we need to make. We want to make 2 of them. And we want to make them without replacement. So we want to set replace equals false. And what that means is that when we choose the first one, we don't put it back in to be chosen again, because we want the agent and the goal to have different positions initially. And that will make the game not too easy for the agent. It would be too easy if or I should say the hero, it would be too easy if the hero already started at the goal, and it wouldn't be an interesting story. This should do us 2 indices, but then we have to convert them to positions. And so with positions, I think we want to use basically to convert these numbers that sort of represent positions in the interior, to convert that to coordinates, we want to use divmod, which is going to give us the division or the divide and the modulus, which will be sort of like which row are we in and which column are we in. Let's call this div and mod, and we'll say this is jnp.divmod of indices. And the sort of size that we're using to wrap around is obviously size minus 2, because that's the size of each of these interior rows. And so this is going to give us now a pair of, so because indices is a pair, this is going to give us a pair of, this is a vectorized operation, it's going to give us a pair of divs and a pair of mods. And how do we turn these into positions for the hero and the goal? Well, the hero pos is going to be, we need an int array, so we need to just basically say this is going to be equal to jnp.array. Whatever the row index is, which I guess is going to be div 0, because div is going to have one div for the hero and one for the goal. And then mod 0, because that's going to be one modulus for the hero and one for the goal. However, this is the position in the interior, and in order to get that shifted into relative to the 0, 0 being part of the exterior wall, we're going to need to add 1 to this. And that should do the trick. And so that will sort of shift both the row and the column ID up by 1, which will now put us in the interior. And we can do the same for the goal pos. We can say 1 plus jnp.array, but now we need to get the second div and the second mod, so div 1 and mod 1. And that should do it. Now, the last thing we need to do is, it's possible at the moment that we picked an interior place where the 10% chance came up that there was a wall there. For either the hero or the goal, this could happen. And so for both of them, we need to make sure that if there was a wall there, we actually remove it. So we're going to need to modify our walls one more time. And this is just to ensure consistency. So ensure these, I need a comment, ensure these positions are free of walls. And so walls is walls at. And now how can we index the hero pos? That's fine. We just need to use hero pos 0 as the row and hero pos1 as the column for our at, and then we have now the position and we need to set it to false. So if there was a wall there randomly, that wall will now be removed. And then we do the same thing for the goal, avoiding a little bit of typing. We can just set the goal pos and goal pos and set that also to false. I think you could probably do this in one lookup and set them both to false at once, but this is also easy to read here. And so let's see, we're now ready to return an environment, which, remember, an environment is going to have a hero pos, a goal pos, and walls. So we've got all of those components, so we can put this together. So hero pos equals hero pos, goal pos equals goal pos, and walls equals walls. Walls has been through many updates, but the final version is with all the modifications, and that's the one we want to add in the environment. So now we have enough to initialize this environment, and actually I guess we could, before we implement render, we could make sure this is all working by just printing the state itself, which is just a bunch of arrays. So let me move from here into lecture 9 and then run my environment and see what happens. So okay, so this is not exactly very pretty to look at, but you can recover from this that we have done what we wanted. So we took we have an environment object, and we have a hero pos, which is an array of int32s. 6, 1 is the location in coordinates row column of the hero, and then goal pos is 6, 6, and then so it's in actually the same row but a different column, little bit to the right of the hero. And then that's also an int32. And then we have this walls Boolean array that you can see, which is pretty big and pretty hard to see. It would be interesting to maybe sort of print out state.walls as type int, which would then turn these into zeros and ones. It might be a little bit easier to see. There we go. So you can see here we have the exterior walls set with those ones, and then there's a few positions in here that are set to 1, and let's just double check that if we go to 6, 1 and 6, 6, so this is 0, 1, 2, 3, 4, 5, 6, and then 1, this must be where the hero is standing, and 1, 2, 3, 4, 5, 6, this is where the goal is, and there are no walls there indeed, and all the hero has to do is move over to get to the goal. Pretty easy. So let's see if we can actually render a better picture than this and then see this in action. So we decided that we want this state.render method to return a picture that represents the state. And so let's see how we could do that in JAX. And there hasn't been any branching yet, but we are working up to it. And I guess you could see that there's some examples of sort of avoiding branching here, in that I didn't say something like, if there is a wall here, set it to false. I just set it to false. And if it was already false, then that's kind of just like a redundant operation. Sometimes in JAX, you can just avoid branching by just doing something that is going to be a no-op if it wasn't needed. It's going to be kind of redundant, and that's okay. And so when you can avoid branching, you might as well do that. That is sort of a good trick. And then let's go on to rendering. And I don't think there's going to be much branching here either, but we'll get to it soon. So jax.jit our def render, which will be a method that takes self, and that's all it needs to take. But the output should be, I'm undecided. I guess we want a float array. Matthew.lib can take float arrays or uint8 arrays for plotting images. So let's just make it a float, and then I guess we know how to interpret it. And we want it to be size by 3. So size by like RGB channels. Okay, so how can we turn our self, which has this walls and this, it has walls and the position of the hero and the position of the goal, into an image? We probably want the image to have some, I've decided here that we want the image to have the same size as the world in terms of pixels. So it's going to be like a pixelated image where there's 1 pixel per position. So it's going to be quite small, but when we print it out on the terminal, it will be enlarged. And then when we print lots of these, we'll be able to fit lots of them in one image. So that's not a problem. And we could upsample it if we wanted. Anyway, so we want to maybe, let's just start by figuring out what the size actually is so we can create this image. And so we need to figure this out statically, by the way, but that's okay because we can get it from the shape of the walls. So self.walls.shape0. Shape of walls is size by size. So we can take either 0 or 1 here as the size. And then we could create a blank image and we could see about how to fill it in. So let's start by that. We'll call this image RGB, and we'll say we'll take JNP zeros to start with. and we'll take the shape that we want. So size by 3. And then we need to sort of set out where we want the walls. Where there are walls, we want the pixels to have one color. And where there are no walls, we want them to have another color. And I guess black is a good background color to have. It sort of is going to work with the terminal very well. And that's what zeros will achieve. So we just need to set, when there is a wall, we need to set the color to something else. So let's do it like this. So we need to modify RGB. So we need to actually override it. We've got a problem now because now actually we do need to branch. So I was mistaken when I said we didn't need to branch. We need to branch because we need to basically set this array wherever there is a wall. We need to set it to one thing, and wherever there's not a wall, we need to leave it as it is. So how would you do this in NumPy, for example? In NumPy, you can use Boolean indexing to kind of selectively grab part of an array and do an assignment there. So what that might look like is something like this. You might say RGB walls or self.walls, which is not exactly going to work, but let's just pretend that, you know, conceptually this would work. And then you could say, we'll set that to, I don't know what array we want to use, jnp array. What color we want to use, maybe 0.2, 0.2, and 0.4. And this will be like a nice dark gray blue color. Basically, you could do something like this in NumPy if you had a Boolean mask for your array. However, this is not going to work if you think even conceptually in JAX, because first of all, not just the mutation, but even if we did a version of this with set, it's not going to work because it's going to be trying to set a size, a number of cells in the array that depends on the values of the array. So this is basically an example of a shape that depends on the values, and we know that's not allowed. This will be an invalid computational graph that can't be determined at trace time. And so this is not going to work. We need some other way to do this. And there's a couple of ways. And let me just show you in the JAX documentation a few primitives we could potentially use here. And so the first of these is called jax.lax.cond. So jax.lax.cond says it's going to conditionally apply one function or another function depending on the value of a predicate. And the predicate is supposed to be a scalar, so it's supposed to be a Boolean. So we could, in principle, go through the various entries of walls, and when that predicate is true, when there is a wall there, we could apply one function, which would be maybe like generating and returning the color for a wall. And when it's false, it would generate another color, maybe black, for no wall. And then basically you can see here the sort of pseudocode for what's going on. If the predicate is true, it's going to apply the true function and return the result. And if the predicate is false, it's going to apply the false function. And so this could work. However, note that this has to be a scalar, so we'd have to somehow like vmap this or something like that over the entire object. And then it basically says that it's going to, when transformed with vmap, cond is converted to select, which is the sort of vmapped version. And so we can talk about select instead as like a slightly more appropriate version of this. Now, here's select. So select is basically the same, except instead of taking functions that you're allowed to sort of pass in operands, we can instead just pass the array of results that you would get. So this is interesting, and we'll sort of talk a little bit about what the important difference this implies is. But this select allows us to basically have an array of predicates. Predicate is now allowed to be a Boolean array. And then there's an array corresponding to entries where the corresponding entries in the predicate array are true, we should use the values from this array. And when the corresponding values of the predicate array are false, we should use this array. Of the predicate array are false, we should use the on-false array. So that is more like what we want, although the on-true and on-false and predicate all sort of have to have the same shape. So that's a little bit awkward with this RGB setup, but we could maybe add an extra dimension and like replicate the trues and falses of the walls to have a third dimension of like just replicating like true, true, true for RGB. Or false, 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 and then that would in principle do the trick. However, one difference here that I'm noticing also, just to make a remark on this, is that In general, select leads to evaluation of both branches. So we have to know on true as a full array and on false as a full array if we're going to pass them into this function in Python. And what it's saying is that it's actually also not going to be able to mostly lazily evaluate that internally after compiling either. That's sort of what this is hinting at. And so if it's possible to elide some of the computations and not perform some of the computations, the compiler will do that. But in general, you should model select as it's going to evaluate both of these things and then only do the one that matters. That's not the case for cond, but it is important when we're vmapping or when we're doing like a big comparison. We still want the computational graph to basically only depend on the shapes. And so the easiest way for JAX to sort of ensure that is that it's just going to evaluate all of the inputs and have them ready, and then just select the parts that it wants. And that selection operation is something that it can do on a GPU. There's sort of like special primitives for doing that. That is going to mean that we're kind of doing both branches and then just picking the part that is needed. And that is the way to keep the computational graph the most uniform. So even if we don't need a whole bunch of one of the branches, we still compute it, because maybe if the values had been different, we would have needed it. And so that computational graph will be more flexible. Okay, so these are two different ways, and I guess select is a little bit more appropriate in our case. But most of the time when you want to use select, you actually end up using numpy.where instead anyway. And so numpy.where, jax numpy.where. So where is a function that exists in NumPy and has the same functionality, but it's normally used in a different way. So in NumPy, you normally use like a one argument version of where you give like an individual array, and it sort of gives you back some indices about where that thing is non-zero or truthy. This is not normally the way that we do it in JAX. In that, you would want to use something else. However, there is multiple versions of numpy.where if you provide different numbers of arguments. And the version that is most commonly used in JAX is the version where you provide one argument that represents a predicate, and then other arguments that represent what to do where the predicate is true and what to do where the predicate is false. So it's a bit like select in that case. And it sort of says here that this version of where, jax numpy.where, lowers to jax.lax.select. So this is like a higher level version of where it's not so pedantic about the types. It can do a bit more casting, a bit of broadcasting. And so this is going to be normally more flexible for use and more kind of ergonomic for use in the code that we're writing. And so that's also going to be the case today. We're going to basically use numpy.where. So let's see what it takes. A Boolean array, which is broadcast compatible with x and y when x and y are specified. And then x should be an array-like, which is broadcast compatible with the condition and with y, and typecast compatible with y, so it's going to do some typecasting if necessary. So it basically has to know what the output type is going to be. That has to be like known at compile time, because that's going to be part of the computational graph, of course. And y is likewise broadcast compatible. So I think the other values are not going to be used in most cases where we're using this 3-argument version, so we'll ignore those. And just look at the return. It is going to have values drawn from x where condition is true and from y where condition is false once you've like broadcast everything. And so that seems good. That's what we want. And then if x and y are none, then we're dealing with the other version of the array of this function where it doesn't have 3 arguments, and so let's ignore that. Let's go back to our code and sort of say, how can we recover from this? So instead of doing Boolean slicing or like Boolean masking, we're going to use where. We're going to use jnp.where, and we're going to give it self.walls as a predicate. And we're going to say, okay, great. Self.walls is a predicate, and where that predicate is true, I want you to use one value of the colors, and where the predicate is false, I want you to use another color. So where there's a wall, I want you to use jnp array this, and where there's not, then you can just use whatever was already in the RGB array. Just keep it the same. And so let's just double check that everything here is broadcast compatible. And unfortunately, I don't think it quite is. Because have a look. The shape of this is size by size by 3. The shape of this is just 3, so that's broadcast compatible with size by 3. This will basically broadcast up to a whole grid of this color. But walls is not broadcast compatible with those because it's size by size, and we broadcast from sort of the last dimensions back up. So in order to make this broadcast compatible, we would need to make this walls size by 1. And so let's just do that. Let's make it size by 1. One way to do that is to, there's a few ways I suppose, but to add some colons and then put a none axis in. And this will add a third axis, so turning it from size by size to size by 1, which is what we need. And now this is broadcast compatible in sort of the other way from this one. And this should work. So we're going to move on and see what else we need to do, and then we'll see this in action in a moment once we've finished putting in the hero positions. Actually, I guess we could test this already. So let me just return RGB, and we can put the hero and stuff in. I better spell it right. We could put the hero in later, and we'll see what rendering looks like. Hey, that looks pretty good. So we've got this map that we had of 1s and 0s, but now represented with no errors, and it's all jittered with pixels. So that's great. Okay, cool. Let's move on then and draw the hero and the goal. This is not going to involve branching. We can just directly index, kind of like we did up here, and we can say RGB at and so on. So let's do that. RGB equals RGB.at, and we'll say hero pos 0 and hero pos 1. And at that hero pos, we want to set the RGB array to something, some color that we can use to represent the hero. Well, I like cyan, so I'm going to set this to cyan. jnp.where of a particular color, and this is just an RGB, so I'm going to use no red, all green, all blue, and that gives us cyan. Okay, we can do the same basically for the goal. If we duplicate this code, and then instead of hero pos, we're going to use the goal pos. Oh, I guess I should make both of these actually self.hero pos and self.goal pos. Like we had self.walls up here, so that's my bad. And then let's make this all red and all blue, so that will be magenta, which is my other favorite color. And so there we go. So we've put, like we said before, the hero is sort of sitting here and the goal is sitting there just to the right. So this looks like a successful rendering of the environment, and I think we're done with the render method. So we've learned a little bit about branching and NumPy-where, and we're going to continue now implementing this environment. We want to basically make this hero be able to move around the environment, and that is going to require responding to some actions and checking for collisions. And this will sort of superficially look like the kind of thing you would do with branching, like if statements, but instead we're going to be able to figure out how to do it in a way that's compatible with JIT. So let's move on to that. And the thing that we want to do here is basically we want to check, we want to do a step method. So actually, I guess I want to go back to sort of designing the API for this. And what should that API look like? And so one thing we could do is we could go back up to the main function, and we could see after we've rendered this, what if we took a step? So in fact, what if we took a random walk? And we were somehow sort of randomly choosing an action and then applying the action and then seeing where the hero was going to go and so on. And so let's see about that. So if I say we just maybe go wild shrew and we want to do this like a bunch, then we want to take a step. And so we want to maybe take a random step. And so we should say we need a key for our step. And we'll split that off from the main key. jax.random.split key. And then we're going to need an action, which I'm going to use an integer to represent different actions. And I'll do something about this in a moment to make sure we know which integers are which actions. But we'll just first get a random integer. And I'm going to make it that there are several actions that you could take. And one of them is going to be standing still. And one of them is going to be moving up, left, down, and right. And so that's 5 actions total. And then I guess I should say a equals 5. And then I just want a single action, so I'm just going to ask for a scalar here. And now action is going to be an integer that is either 0, 1, 2, 3, or 4. And depending on which of those it is, we're going to be wanting to move in a different direction. And then I want to actually take this step. So I want to get a new state of the environment. And I want to say that state is going to be equal to the old state step. And I want to supply the action as input. And that should probably do it for the API of taking a step. And then I guess I would want to print mp.image of state.render after I've taken the step, and then maybe make sure this doesn't go too fast. So I'll time.sleep 0.02. And in fact, I guess I should do my trick here of actually making this an animated plot. So I should say the plot equals mp image, and then I should print our scrubbing minus plot, and then plot. And then let's see about this. Of course, we haven't implemented the step method, so this isn't going to work. But let's go and implement it now. So let's add another method after render, and let's call it step. And we want to make sure everything is jittable, so let's start with jax.jit. Oh, sorry, jax.jit, not jit.jax. And then def step. And we said it should take self and an action. And the action should be an int. And then it should return, I guess, also self, because we're going to return a modified version of the state. Everything is immutable, so it's not like it can internally update the state of this environment. It has to actually return a new version of the state. And so this is an appropriate API for that. And now we're going to need to actually implement this. But first of all, I guess we need to decide on a convention for which numbers mean which actions. And one convention that you could use is the following. Let me just see how I did it in the code to make it all consistent. And we're going to define a new enum. So let's just make a class action, and let's make this an int enum, which means it's an enum when we want to use it in code, but it's also functionally an int if we want to like put it inside an array or something like that. And we can have a weight, which corresponds to 0, and then up is 1, and then left, I'm just going to do this in like WASD order. Left equals 2, and then down equals 3, and then right. So WASD would be up, left, down, right, and so that's the order I've got here. And weight is special, it's 0, but I guess that makes sense. So this is going to be our actions, and I guess I could say this action is not only an int, but actually an action, which is like a specific type of int. So that should work, I think. And then we have to actually implement the step method, which is not too complicated, but it does involve a little bit of thought to how to get this to work with where we would apparently need branching. So the first thing we need to do is make sure that we figure out where the agent is trying to go or where the hero is trying to go. I keep saying agent, thinking of RL. Where the hero is trying to go when we take one of these steps. And so one thing you could do is you could have something like if action equals action.wait, then do nothing, and so on. But we know that these if statements aren't going to work. We want this action to be able to be, we don't want this to be static. We want this basically to be something you could like sample from a policy and put in to this function, and you could be v-mapping over a bunch of different actions in a bunch of different environments and so on. We don't want this to be static. We don't want to concede that. So we're going to need to find a way to make this happen independently of sort of the value. We need the code to look sort of the same. And so one way to do that is to use an array of deltas and then index into the array. And the deltas represent like what change you would make to the position. And we index in with the action to get which change we're going to make. And then we'll apply the change to the state or the position. And so here we go. So let's call this array deltas. And we'll say it's JNP array of all the different things that you could have be the change if you were taking one of these actions. So the first one should be corresponding to weight. And we'll just say that if you wait, that would mean that you would sort of move 0, 0. You would move by 0, 0. You would sort of update your column and your row, or your row and your column by nothing. What if you move up? So that's our next action, and so this should be the next thing in the array. Well, then that's going to correspond to kind of decrementing your row so that you go up in this table. So we'll have -1 in the row section, and the column stays the same if you're moving up, so that's that. And then what about if you're moving left? Well, that's going to correspond to decrementing the column. And then if you're moving down, that's going to correspond to incrementing the row. And if you're moving right, that's going to correspond to leaving the row the same and incrementing the column. And so this array represents what happens if we wait or move up or left or down or right as a delta on the position vector. So we should basically be able to say that the new hero pos is equal to the old hero pos, self.hero pos, plus deltas. Actually, that's not required, right? It's plus deltas and then index with the action. And that gives us the specific delta that we do. So there we go. So there was no branching involved here. There was only indexing. So we kind of avoided branching by doing indexing. And that is one trick that you can use if you want to branch on an integer. And especially if it's a small integer, or if you can map it into a small range. You could have an array where you represent all of the possible values that you want, and then you use indexing to get the value as if it's in a lookup table. I guess we did something similar in the overture, really, when we were talking about finding the next state. Instead of conditioning somehow on what the neighborhood was in the cellular automaton, we used a lookup table of these booleans. And so you looked with the, well, they weren't booleans actually, they were small integers, so we could use them for indexing, because it's hard to use booleans for indexing in JAX, as we explored earlier. And so, yeah, this is one thing. The problem is, if we now were to, let's see, if we were now to sort of say, okay, well, let's now return this sort of data classes dot replace of the state, making this update that the hero pos is equal to the new hero pos. Something might go wrong, and that is, so I wonder if we'll be able to see it. I guess it'll be interesting to see if, okay, we have to define our action before we define our environment, so we can use it in the type signatures in this version of Python. Can't wait to upgrade to 3.14, where I think that would not be the case. But anyway, okay, now so I've done this wrong. I did jax.jax, and then I did jit.jax, and then I did jax.jax. What I really need is jax.jit. Finally, will I? Okay, this is still not working. Okay, sorry about that. Self, this is supposed to be self. Anyway, yeah, so now we have a problem in that it looks like the agent, the hero is able to walk through walls. And so we've forgotten to implement collision detection. So let's do that now. And we'll just let him walk around a little bit at 50 frames a second. I did put it in the time.sleep, didn't I? Yeah, okay, cool. So it's not going to burn my CPU too much. Oh yeah, he's way gone off the map, and I wonder if he's going to come back. We'll have to quit and start again. But anyway, we need to do some collision detection. So this new hero pos is like a little bit suspect. It might be where a wall is. So we need to basically check if there's a wall there, and if there is a wall, we need to revert to the old hero pos again. So that is going to sound like a branch again, but we're going to learn how to do it without a branch. Hey, he's back. I don't understand why he's sometimes there and then sometimes there. Oh, you know what? This might be even really bad because we're sometimes using a hero pos of negative and then it's using negative indexing. So that's even worse. There you go. I'm surprised we're not getting index out of bound errors when we try and render, but I guess I shouldn't be surprised because JAX does not respect out of bound errors. And if there's an out of bound error and you try and render something, if you try and index into an array out of bounds, it kind of just does nothing. So watch out for that. You should always make sure that your indices are valid when you're indexing JAX arrays under JITted code, because it doesn't do any bounds checking. Yeah, okay, watch out for that. Anyway, let us continue with this code. So where were we? So we're trying to do some collision detection. This is what it takes to actually move the hero. And what we need to do now is like check for collisions. And so if there is a collision, then we want to revert back to the old hero pos before we moved. And so let's do that. So basically, we want to see if there was a collision first. I think that's going to be a good start. So collision is going to be equal to, it's easy enough to look up in the self.walls at the new hero pos. We can look up new hero pos 0 and new hero pos 1, and if this is true, then that means that we're currently proposing to move into a situation where there's a wall. And so this collision is going to be a Boolean, because this is an array of Booleans and we're indexing into it, and this is going to be true. So what can we do with this? Well, one thing we could do is we could use jnp.where, and if this is true, then we could use a branch that corresponds to the old hero position, and if it's false, we could use the new hero position. So let's do that. So let's say the new hero position after checking for collisions is going to be equal to jnp.where of the collision. We already learned about jnp.where when we're doing rendering, so this is just going to be a similar use as that. If the collision is true, then that means that we have collided, and we don't want to do this move. We don't want to keep this new hero pos. We better go back to the old one, so we'll use self.heropos. And if the collision is false, that means it's fine. It's fine to walk here. We can walk here, no problem. We can just say, let's take the new hero pos as the new hero pos. And so we'll keep the new hero pos basically. And so let's just double check that everything is broadcast compatible here and typecast compatible. So this has to be a Boolean, and these have to be typecast compatible, where they're both int32 arrays of size 2. So they're both the same as each other. But are they compatible with this Boolean? They're not typecast compatible. That's okay. They don't have to be, but they are. Well, then maybe they are typecast compatible. But anyway, they are broadcast compatible, and that's what matters. And why are they broadcast compatible? Because this is a scalar, and scalars are broadcast compatible with anything. So that's one really cool thing, is if you have a single scalar and you just want to choose between using two different arrays in the next part of your code, you can always use jnp.where, and it's very easy because you don't have to worry about broadcasting, because this collision Boolean, this scalar, will scale to anything, and you'll just take the whole, you'll just broadcast over the whole array, and if it's true, you'll take the whole one array, and if it's false, you take the whole other array. And that's what's going to happen here. So this is the perfect tool for the job. And then I think we can just move on with our code. So let's quit this guy. This hero is never coming back. That's a sad ending. That's a tragedy. So let's start again and keep them actually bound to the arena. And looks good. One problem I'm noticing, however, we're ready to move on to the next thing, and we've got this working, is that I think I saw the hero hit the goal, and then nothing happened. It's not a little bit, it's like not exactly clear when he hits the goal, or when they hit the goal, but I think it's, yeah, oh, well, that was clearly hitting the goal just then. I don't know if you can see as many frames as I can see in the recording, but I swear I saw the hero hit the goal, and nothing happened. So we don't want that to be the case. We basically want to make a section in our random walk that is going to notice if the goal gets hit, and then reset the environment to go to the next version of the maze and make the hero find the goal again. So let's set that up, and that's going to involve another example of branching. So in order to do that, we're going to need to detect if the goal has been hit. So reset if goal hit. I guess we're going to need to know if the goal has been hit. So what if we had an API for that? That was going to be, we're going to have a reset variable, and it's equal to state.goal. And state.goal maybe can be a method that checks if the current state, if the agent is, or if the hero is in the position of the goal. That sounds good. So let's go and implement that straight away. So that's going to be easy to check. Okay, so like it's not like you have to check, oh, if the thing is, if the hero and the goal have the same position, return true, and if they don't have the same position, return false. You can just directly evaluate, do they have the same position? That will give you a Boolean, and you just return that Boolean. So you don't need to branch or anything like that. And we can just jax.jit this just because it should be easy. So def, although it's a very small function, it's not really going to make sense. We'll have goal, and we'll have self as the argument, and we'll have the return as a bool, and we'll just check, is the current hero pos the same as the current goal pos, and we'll just compute that as a Boolean with an equals operation. And so we'll return hero pos, or self.hero pos, self.hero pos equals self.goal pos. Only this would give us actually a Boolean array of size 2, because this is an element-wise equality check. So we actually need to do jnp.all to make sure they're all true. It's true in the columns, and it's true in the rows, or rows and then columns. And so that is the first step. And that should do the check. I think that's it's as simple as that. It doesn't need to be more complicated. Yeah, that's what I've got in my my cheat sheet. Okay, so next we need to worry about what to do if that is the case. And this is going to be an example where, if we go back up to this loop, where we need to do something, we need to sort of proceed with a state. We need to proceed with one version of the state if the goal is, if the goal was hit and reset is true, and we need to proceed with a different version of the state. We can kind of continue with the current state if the goal is false. So, as in if the goal has been hit is false. So one thing we could do is we could sort of just prepare a new state just in case, because normally we're going to need this new state. We're going to need to compute it anyway, just in case, because we need to make sure that the computational graph has room to compute it in case it is actually needed. So we'll have the new state, the potential new state, or something like that. We'll just re-init the environment. Init, we need to make sure we use the same size and everything like that. We're going to need a key for this, I guess. So I'm going to need a key reset. Key reset, key equals jax.random.split. And then we'll put key reset here. And then we'll make sure we use the same size as we had before. So size equals size. I've still got that coming in from Tyro. And then basically we need to proceed. We need to make sure that at the end of this, we have state, which is equal to basically just pseudocode here. I want to say the state is equal to the current version of state if not reset, else it needs to be equal to new state. And obviously this isn't going to work. Well, I guess this would work actually because we're not inside JIT. But let's not do it like this. Let's do it the proper way so that we could do it if we were JITting this loop, which we will try and do in a moment. So we're going to need to do this the proper way. So what can we use here? Well, I guess we could use where again. Because we have a single Boolean. And so when you have a single Boolean, it's normally broadcast compatible with everything, right? So let's just try that. Let's say state equals jnp.where, and we want to put it as if reset. Then we said we wanted to have new state, and otherwise we wanted to have the current value of state. And so should this work? Let's try it and find out. I think we're going to get an error though. Okay, so here we go. So here is an example of an error that you might sometimes see, and it just means we forgot something. So let's read the error. Where requires nd array or scalar arguments and got class main environment at position 1. Okay, so this is an issue. This is a case where I said reset is a scalar and it's going to broadcast over everything. It's not quite true because it's not going to broadcast over a pie tree. An environment is a pie tree. And so we actually need to make sure we do a tree map here. And for each of we need to have the new environment, and we need to basically create this new environment, and it needs to have all of the components of an environment be selectively decided between different whether it's the one from the reset environment or the one from the old environment. And so tree map is the way to do that, but it's a little bit annoying. So let's just do that. jax.tree.map, and the tree map is going to be over lambda between the old and the new. If I could spell lambda, old and the new, and it's going to be jnp where reset. Where reset we take the new, and where not we take the old. And then the old is going to be the state, and the new is going to be the new state. And now we're going to tree map this, and for each component of the environment pie tree, we're going to go through with this lambda, and we're going to take the old and the new and pass them in, and we're going to keep the new one if we want, and the old one if we didn't reset. And so that should now work. And now every time we eventually hit the goal, it's sort of taking its time, but he will eventually hit it. I've seen it. There we go. So then you see the environment reset. And then sometimes the hero is faster at hitting the goal than others, but that's just luck because it's not a very smart hero at the moment. It's just randomly walking around. Okay, so we're going pretty well. We're nearly done exploring this. I would just like to do one more thing, which is basically accelerate this entire loop to give us another example of accelerating a loop in Python. In this case, I guess we could use for/i or scan. And then I think we're going to be doing some fun stuff with V-mapping it and making a very compelling demonstration of a lot of different heroes looking for a lot of different goals in all sorts of different random ways. And so let us see what the next step is there. So I basically want to replace this loop here. We can keep this loop in the code for posterity, but I basically want to take a version, I want to basically make a version of this that just sort of commenting that. I want to take a version of this that is going to be a function instead. And then I can JIT it and I can VMap it and so on. So let's take it and let's make it a function and let's call the function walk. So def walk, and I want to be able to JIT this function, I want to be able to VMap it and so on. So we'll make sure that it has nothing, we might flag certain things as static. What arguments do I want for the function? I guess what are good arguments for a random walk? Well, maybe one of them would be we would want a key so that we can do some randomness. So how about that? How about we start with key, which is a PRNG key array. And then how about we decide how far we want to walk, how many steps we want to do. So maybe like num steps, which could be an int. And we're going to probably need to make that static because if we're going to return the trajectories, it's going to depend. And even if we want to just like decide how many iterations to do, we're going to need to know num steps. And then we should probably also know the size of the environments involved. And that is just going to be coming up from before. That's our like 12 or whatever. So then we can certainly need functools partial for jitting this, jax.jit, because it's going to have some static arguments. So arg names, in particular, walk and size and num steps are going to be static. That just fits. And then key can be okay. We know that we can jit over keys and so on. They're dynamic. And then yeah, what's the return type, which I haven't added here? Well, the return type, let's make it an environment, but in particular, let me try again. Environment. But in particular, I basically want this to be not just an environment, but like a batched environment. I want to make it an environment where we have a time dimension to it. So it's going to return basically an entire trajectory of environment states, and that should be good. So basically, then I want to keep this walk, but I also want to keep some of the initialization logic from above. So I'm going to copy that down too. I'm going to start by initializing the environment. And I'll fork my key, that's fine, and I'll set this to size, that seems fine. I won't do the visualization because that can't happen from inside a jitted function, seeing as printing is a side effect. And then I want to define like one step of the random walk so that I can later scan this. And then a step is just going to be, it's going to have some carry as input and then some input, and I think we're not using the input, and so I will just name it like that. And then we actually will take a step and reset if the goal is hit inside this. So this is what was inside of the while loop, and we'll get rid of the visualization logic. And so what's going on? So what is carry? The things that we need to carry, I guess, is the key and the state. So they come in and they come out. They get overridden by the next thing. So we better make sure those are in the carry. So key state equals carry. And then on the way out, we got to return the carry and then also an output. And so we'll return key state, and then we don't need any output, or do we? I guess we want the state as output so that we can accumulate all of these states later into a big array or a big batch of these environments. So if we output the state with this, we're going to scan this. If we output the state, then we'll be able to access the full history of all of those states later. And this is a pie tree. That's okay. That just means it's going to batch automatic. Scan is automatically going to batch this within the sort of leaves of the pie tree. Okay. Let us then move on to actually doing the scan. So jax.lax.scan, we're going to scan the step function, and then we need to provide the initial carry. So that will be just key and state, I believe. And then we need to provide the length or an array of inputs. And in this case, we don't have an array of inputs, so we have to provide the length as num steps. And that's why this needs to be static. And then that should do it. But then what are the outputs? The output is the final carry, which we don't need, and then the outputs are the states. And then, so we'll mark that as unused, and then we have this. Okay, so the initial carry, did I do? So I did the initial carry, yes. Okay, so now I have state coming up here, and I have states coming out here, and they represent basically the initial state and then all of the other states that were like the next states. And I guess if I was to follow the naming convention from back in the overture, I would say this is called next states because this was always next states. And we actually called this next state as well. So next state and then this is next state and next state. And maybe there were some other places where we called it next state, but I'm just going to change that for now. And so we want to basically return a concatenated version, jnp.concatenate of I guess state and next states along axis 0. But of course this isn't going to work because, similar to before, these are pie trees because they're environments. And so we actually need to do this concatenation at the level of each of the leaves of the pie trees. And so we need to do this in a tree map. So let's do jax.tree.map of a lambda that takes a leaf and a set of leaves from the next states, and then concatenates them, and we'll say L L none, because we need to actually add an extra dimension to be the time dimension. And then, because this is just a single state, and then we'll have L's. And so we concatenate those along axis 0. And then we're going to map that over state and next states. And that will be what we can return. That will be the states that we can return. And that should work. How to actually get this to happen? We've got this while loop here. Why don't we just skip that while loop, and instead we will do, okay, I had a slightly more elegant way of doing this in my solution where I just took this and left it. Oh no, okay, let's just do it like that. And then we can basically call this for, to get one of these environment batches. But what I want to do is actually vmap it and get a whole bunch of these at once. And so let's do that. The easiest way to do that is to just say that all of the states, I want to have states, or I guess I want to have state, and then it's getting a bit complicated, so I'm going to have a convention of suffixing my variable with what the dimensions are. And so I want to say we have a batch dimension and a time dimension. And the batch dimension is going to come from vmap. So let's jax.vmap, vmap the walk function. And the walk function takes various inputs, so we better make sure we are carefully about which ones of these we're vmapping over. So we want to take the in axes, we want to make sure we vmap over the key, so that we have different randomness in each walk. And then we want to don't want to vmap over the size or the num steps. They're static anyway, so we can't vmap over them. And then the output can be axis 0. That's like normal. And so we sort of were getting an environment timeout, but we'll get an environment batch time instead. And so then we want to actually call this with some keys. So instead of, what keys do we want to use? We have our key, and I guess we can just fork our walk key, or walks key, or key walks. Key walks and key is equal to jax.random.split of key, our ongoing key in the main function. And then we want to split it again. So for each walk, we need an individual key. So let's jax.random.split. How many of these do we want to do? I don't know, 256. Oops, I got to put the key in. So key walks and then 256. And then I suppose then we should just put in some values for size and the num steps. So num steps, I haven't got this as a command line argument, so I'll just make up a number of 512. So this will do 512 steps in 256 environments, all in parallel, although individually the walks will be happening in series because we're using scan. And so this should give us a lot of states in our state BT. And then I have prepared a function that is going to basically save these. So let me add some printing. I'm going to say print doing random walks, and then I'm going to say print saving, and I think I called this save animation, and it just takes state BT as input, and then it will save it in a file called output.gif. But this is not right. So environment. Okay, so because this is Python 3.13 instead of 3.14, I'm going to need to move this walk until after the environment, so that the environment is actually defined in time. And then I guess I should be able to actually run this. Okay, it's doing the random walks. It's saving them. It's taking a moment. Okay, so if we open output.gif, let's see what we see. Hey, let's go full screen on that. Look, we see a lot of different heroes, and some of them are finding their goals. And so that is what you love to see. This is the hero's journey again and again in an infinite repeating grid. Well, it's not infinite, but if we did this for more than 512 steps, if we did it for an infinite number of steps, and then every now and then you see like a little flicker, and that's it sort of going back to the start of the 512 steps. But each individual hero is sort of trapped in a little box, looking for the goal. I wonder if we can see any of them. It is possible that the walls could be configured such that it's actually impossible to reach the goal. Sometimes the goal is unreachable. I can't see any of those cases yet, but I might be missing some. I'm not looking at all of them in detail. Anyway, there we go. So that's our little game. And so that is basically a whole bunch about branching, and then a little bit about branching in a big scanned vmapped loop. and how it all happens really fast on the GPU in principle, although at the moment I'm using a CPU on my Mac. And so let's wrap up. And so I'll just sort of leave this here having a little bit of fun here, and I'll start talking to you about the challenge. So the challenge is going to be to get some extra practice with branching, and in order to do that, I would like you to consider how would you add some extra features to this environment. So at the moment, there's really just a hero and a goal. I would like to see the hero have to go through some steps other than just moving around in order to find the goal. And one of those steps could be that they have to unlock a door, for example. And so you can make it that there is maybe a goal is hidden inside a box or something like that has a lock, or maybe that you could design an environment that always has a wall in the middle, and you could sort of set that up in the generation code, and then you could have it that there's randomly along that wall, that wall somewhere there's a door, and the door needs a key, and the key is sort of somewhere in the environment, and the hero has to find the key, pick up the key, and then you're going to have to do some things about branching. Like you're going to have to make sure that if the hero hits the door and has the key in this sort of inventory, then you can proceed and unlock the door. Otherwise, the hero has to keep looking for the key and can just sort of bounce off the door as if it was a wall. And this is a good opportunity to do some various branching practice. So I'll leave you with that, and you can have fun with this little code base. Yeah, cool. And then I'll see you. Good luck with the challenge, and I'll see you for the next lecture. Bye.